All right, so we're going to be pausing a little bit before we continue with combinations. And this applies to both perms and coms. This is on page 39 of your booklet, so you might want to get that ready. So we're going to be talking about the ways of solving problems, either using direct or indirect reasoning. And I'm going to tell you off the bat that indirect reasoning is what I want to introduce here, because it will save us a lot of time and trouble when faced with certain scenarios. So what you want to watch for is for the keywords. The main one here is at least, or some sort of inequality, right? Greater than, less than, or something that indicates that there's more than just an exact amount. So for example, we just did like creating teams or groups with exactly two juniors, let's say, or two seniors. That's an exact amount. But when it's indicating that it could be, at least one senior, let's say, that is telling you that scenarios where you have one senior or two seniors or three seniors, like it requires multiple steps to even get there. So indirect reasoning is going to help us in that sense. So what's the difference between the two? Direct reasoning, I think the name says it all. You find all the cases, you add them up, and then you get your total of possible scenarios that apply. Indirect reasoning, right? That's different. You find the case or the cases, it depends on the scenario, that do not apply. And then we subtract it from total possible outcomes, right, to get your answer. Maybe up here, how about we, just to clarify, it made sense when I typed it, but you add up all the cases and then you get your answer so that you're not mixing up the total here. That just changes to answer, right? Indirect reasoning, find all the cases that do not apply, subtract it from total possible outcomes. We'll take them away. And then what's left is our answer. So that's what we call indirect reasoning. You actually do that when you're finding the third angle in a triangle. You have 180. You're like, oh, well, one angle is this, the other one is that. Well, let's just take that away from 180 to get what's left over, right? That's indirect reasoning. So it's very helpful in determining instances that are where you just determine what doesn't fulfill the requirements, and then off you go. So this is I'm basically going to give you a formula here. This is the most popular scenario. Determine, this is in general, determine cases with at least one ... When you see that, when it says, hey, find these number scenarios where you have at least one repeated letter in the password or one repeated number in the password or so forth. That's when you would use this scenario. So you would go answer is basically total possible. Okay, total possible outcomes. That's like no restrictions whatsoever. So we figured that out. We've been doing that quite a bit, right? Like how many ways can 14 people line up to take a picture? Oh, it's 14 factorial. That would be all possible scenarios. And what we would do there is we would subtract the instances where it doesn't happen. Okay. So let me just focus here a bit. That the screen is off. Keep in mind, I'm just making this up. Total possible outcomes minus no instance. That's going to give you the at least one scenario, and maybe just follow along with the lesson, and then this formula will make more sense here. So here's an example. Assume we have two events that we're considering. So the first event is spinning a spinner with 4 sections, 4 colors, and rolling a 4-sided die. Now you should already know that using the fundamental counting principle, right, that the first event has 4 options, the second event has 4 as well. So 4 times 4 is 16 possible outcomes. So if you wanted to have all possible outcomes laid out, you would know that there's 16, and there's everything in between, right? Those 16 consider literally every possible scenario. So this is what our tree diagram would look like. I already started it for the sake of time. Okay, so we've got our 4 colors. I chose to start with the colors with a spinner, and then every time you can have 4 values, right? So this would be essentially, if you follow this branch, it would be blue 1, blue 2, so please fill this in, blue 3, blue 4. You're going to be using this a lot in probability. So then it's red 1, red 2, red 3, red 4. And next one is G1, G2, G3. So that's what I mean by writing out all possible outcomes. You actually tell me what the combinations are at the end. White 1, white 2, white 3, and white 4. So these are all possible outcomes. You can say if you counted these, remember you're going by 4, so it's basically 4 times 4. You can really see that here. There's 16 outcomes. Just emphasizing that. And that 16, when we find that, it includes everything that can possibly happen. Okay, just to understand that. This is what we would also know as, or refer to as, our universal set, right? All possible outcomes. So how about now we'll ask some questions here. How many outcomes involve rolling a number greater than 1? So using direct reasoning, we would just go ahead, and I'm going to use, maybe I'll use orange for direct reasoning here on this page. We would just go and find all the numbers that are greater than 1. So over here, we have 2, 3, 4. And then we've got 2, 3, 4, 2, 3, 4, 2, 3, 4. So we will just say, hey, we have direct reasoning would be like, well, we've got 3 outcomes here, got 3 outcomes there, and another 3, and so forth. So that would be 12 outcomes would have a number greater than 1 there. And indirect, how would we go indirect if that's the path you want to go? Well, you take all the cases that do not apply and we'll subtract it from the total. Okay, so how about I just go off here. I'm going to split this. Right, we go total minus no instance, or you can write do not apply. Right? It's up to you. So the total possible outcomes is 16 minus, we've got 1, 2, 3, 4, right? 4 instances, and they're all here. And still you get 12 outcomes. So regardless of how you approach it, that's how it's done. Okay. So that's basically for this page. Let's go on to the next one. You can always pause this and keep copying. And there we go. So here's an example again where I like to have the tree diagram so we can see what's happening. Right, so Fiona is flipping 3 coins. How many outcomes involve flipping at least 1 head? So I'm going to highlight that. It doesn't say exactly, it says at least 1. So that means that we can have 1, 2, or 3 in this case. So here you will also see the extremes. Notice that these are, there's only two ways of going about it in every single event, right? Talking about 3 coins. So at the very top here, you've got the all heads, we would call this branch at the top. And the other extreme down here, we've got all 3 tails. These are important to us. This could also be a true or false quiz or test where you have, a bunch of true and false tests where it's just two options every single time. And you'd also see it as 50-50, right? But here are your extremes, all tails, all heads, and then everything in between, okay? So if you want to fill in this branch, you just follow heads, heads, tails, okay? Then you follow this heads, tails, heads. I guess you can go backwards, right? Tail, tail, heads. So if you want to start tail, tail, heads like that, and heads, heads, tail. Tail, heads, tail. And this one here is heads, tail, tail. And then all tails, right? So could we have predicted, if you look at it, 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes here, okay? Could we have predicted that outcome? Absolutely, right? We would have had 2 using the fundamental counting principle. We've got 2 times 2 times 2, we've got 8 outcomes possible, right? 8 outcomes, and if you count 1, 2, 3, 4, 5, 6, 7, 8, 8 outcomes. It's an important concept to understand, okay? And if the question said, right now it's asking, we want to have all the instances. Remember, this is going to get bigger down the road. So don't go to the easy way right now. Just stay with me on this. You want to have all the instances where you have at least one head, okay? So what I will do here is I'll go indirect, if that's the way I want you to start thinking, indirect. Ooh. 1 second, somebody's, okay, sorry, somebody came in here. Indirect reasoning, again, I'm going to go total, all possible outcomes. Minus, in this particular case, we can go more specific, at least one head. You want at least one head, so we're going to subtract no heads from the total. Okay, that's what I want you to focus on. This is indirect reasoning. So total, we've already determined that it is, I'm going to go 2 cubed here. Okay, we were going to find out that it's a minus, I want you to stay with me here, for no heads. The no heads branch is the extreme here. Okay, I want you to write that down. No heads, right? So we can see it as all tails, but at the same time, we can see it as there are no heads here in this extreme. Okay, so that is always in a scenario like this, it's that one possible outcome here. So minus 1. There's only one instance where that happens. So what should I do here? I'm gonna highlight that as that 1, and then I'm gonna highlight that last row here. So it's in a sense 8 minus 1. So you have 7 outcomes where that is the case. Okay, so it's hard to think of them all, especially when you go a bigger sample. So this is how you want to approach it, right? Total minus no heads. So we took away this one outcome here. So there's 7. So if you think about it, all of these ones have at least one head in them. There's 1 here, there's 1 there, 2 there, 1 there, 2 there, 2 there, and all 3. That's also okay, right? That's at least 1. That's what we're looking for. Let's do like the same thing would apply if this question had said at least one tail. If it says at least one tail, we would have gone 2 cubed minus 1, but that one outcome would have been removing the all heads scenario. Okay. Okay, so let's park there a little bit. If I had flipped, like, let's say 10 coins, this thing would have continued on, right? Indefinitely. Oh, well, 10 coins, that obviously stops, so it's definitely. But at that point, regardless of how far, how many coins you toss, the extremes, top and bottom, there's always one outcome where you have all tails or all heads. That doesn't change. Okay, you gotta understand that. Maybe I'll add a question underneath this for you to try. How many outcomes involve flipping at least two tails? At least two tails. So in this case, it doesn't, in this case, it's small enough, it wouldn't matter how you went about it, but I will go total if you want to go direct or indirect, but I'm going to go total minus no tail, no heads, okay, minus one head. I'm going to subtract all the cases where there are no heads and all the cases where there's just one head, and obviously everything else has to have two or more. So again, 2 cubed minus no heads, we already know it's this one, it's just the one there. Minus all the cases where you have one head. I don't know if I want to highlight, maybe I should. Okay, I'm just going to highlight this one. Let's go and find all the ones that have one head. So there's one, there's one. That has two, right? This has one, two, two, and three. So we're going to subtract the three cases there from it. Okay, so no heads, I guess I can highlight no heads like this and here as well. So we now take away a bit more, right? There are fewer options now because you're putting more restrictions on. So that'd be 8 minus 4, which is 4 outcomes. And you can verify this if you count, right? 1, 2, 3, 4, like whatever isn't highlighted is what we're after. So there it is. Okay. You're wondering how would direct reasoning how would that have worked here? You just go ahead and select this, this. You actually add what you're after, and that would have been 4 as well. So either way, you get to this answer. Let's do flipping coins, but more coins. Let's say we're doing 5. So let's write that down under here. Example. You are flipping, let's go 8 coins. How many outcomes have at least one? Let's change it, one tail. So you can pause this and give us a try if you want. All right. So flipping 8 coins. So coins. So basically you have 8 events. 3, 4, 5, 6, 7, 8. I'm not going to bother making a tree diagram because you would go crazy, right? But you've got 2, 2, 2 every time. A coin, you can't really take away options, right? You've got the same amount every time. This is really 2 to the power of 8. Okay? And so that's my total outcomes. Let's figure out what that is. 2 to the power of 8. That's 256 total outcomes. Okay, there we go. And now we want to answer the question, at least one tail. This is a classic question, like flipping coins or true and false as well. So we're going to say the answer is going to be found by going 256 minus how many instances do we have with where there's you want at least one tail? No tail. No tail is the very top, right? And this tree diagram will be at the very top. I don't know if you want to write that down. No tail. No tails, I should say. Okay, that's the very top. So it's always 1. Okay, take away the one instance, 255 outcomes. Another example, similar reasoning. A quiz has 10 true or false questions. Okay. How many ways can you respond and get at least one question right? And here is the same idea. 10 true false questions. So true and false, it implies two options, just like heads and tails, right? So we would go 2 to the power of 10 minus just 1, that where you get all wrong, right? If you did your tree diagram, and if you do true, false, and then true, false, but you continue this would be all of them right, but if you follow the bottom here, right, if you did this 10 times, if you kept on going along the bottom here, that'd be your one instances where all of them are false. Okay, so 2 to the power of 10, that's 1024 minus 1, so 1023 questions ways, right, where you at least one of them would be true, or one of them would be correct. Sorry, I should say it that way. If you randomly guess, right? So there we go. Let's keep going. If you want to try, well, let's do question 3 here together, because passwords are quite popular. Okay, consider a 3-digit password. How many passwords can be made with at least one repeating number? Okay, so sometimes, and I know I've been there too. I remember in high school, at least one repeating number is like, okay, don't do this right now, but I'm just going to give you, I would just say, okay, well, one repeating number at least. So then I would go 10 times 10 times 9, right? So there I have my two repeating numbers because you've got 10 options. I use 10 again and then times 9 because this one isn't going to repeat it. However, it could be 10, 9, 10, right? Where you don't repeat the second one, but you do repeat the third one. So it goes all over the place. To consider, to use direct reasoning in this case would be quite difficult, and it's actually a small sample still, a small number of outcomes. So with at least one, let's highlight that part. With at least one repeating number, that's what you want. So let's figure out total outcomes. Total outcomes, if you think about it, if you use the fundamental counting principle, we would just say, well, we're assuming it's 0 to 9. Okay, that is assumed here. So 10 digits or 10 per slot. So that'd be 10 to the power of 3, which is 1,000. 1,000 passwords possible. And that would have everything. Repetition, no repetition, it just has everything. And then we're going to go no repetition. We're going to subtract the passwords that would not have any repeating digits. So that would be 10 times 9 times 8. And no repetition in this case. And that would be 9 times 8 is 72. So 720 passwords that have no repetition. So quite often, question on the exam, even on the test, you're going to be asked to find how many possible passwords or license plates or whatever can be made. And then when it says at least, how many with at least one repeating number, well, we're going to focus on the ones that do not have, you don't want to do a tree diagram on this one. It would be quite crazy, right? So we're going to go 1,000 minus 720, and then you're left with 280 passwords. And these have at least one repeating digits. Indirect reasoning, again, I will state that. But that's the way to go with these types of questions, okay? And if you want to try this one, right, I have another password scenario, and then here it is again, to D, right? You have at least one repeating number. How would you do that? Similar idea. So you can try the quiz question as well. Give that a try. So we're going to pause there, and then I'm going to go to, because I just want you to write down notes for now. We're going to go back to 47, okay? Back to 47, where we started to talk about combinations. We're making teams, and I'm going to make some adjustments here as well, okay, as we go. So maybe review this question real quick. We had 5 juniors and 4 seniors, and we wanted to make teams of 4. So you had 9 total to choose from, making teams of 4. No roles, no specific slots to be filled, so we know it's combinations. So no restriction, right? There's 126 possible teams that can be made with no restrictions. You don't care if it's all juniors, all seniors. If it's a mix, it has everything in it. That's called the universal, right? You can remember the universal set from chapter 3, right? That's what it is. And then we're given some restrictions. You have to have an exact number of 2 juniors. So from the 5, we chose 2. And from the 4 seniors, we chose 2 to make our team of 4. Remember that. And you have to have your total of 9. Right? Team of 4, but 5 and 4 still adds up to 9. Exactly 3 seniors. We talked about that one. But then it changes here. And that's why I stopped the other day. At least one junior is on the team. Use direct or indirect reasoning. I'm gonna and it says, I know that, but we're gonna use indirect reasoning here. So what we're gonna do is we're gonna go total teams minus, we're gonna figure out a team, right, or teams without juniors. Okay, because if we want a team that has at least one junior in it, then we're just going to say, okay, the total, which we already have determined, is 126. Then we're going to subtract the team that would have no juniors in it whatsoever. And so we already know this. I'm going to restate this one. 9C4 minus team without juniors. It essentially, I like to always think about it this way. From the 5 juniors, we would choose 0. And from the 4 remaining seniors, we would obviously have to choose all 4 of them to make our team of 4. Okay. And so remember, I already want to kind of prepare you, right, for that it's always both component. You need juniors and seniors. In this case, we picked none of them. Okay, so 9C4 I already know is 126 minus 5 choose 0 is just 1. 4 choose 4 is also just 1. Okay, so it essentially is 126 minus 1. And there we have our answer. It's not always 1. It is not always 1. Okay, so 125 teams. Don't think that it's always that. I was going to give you the long version here, but I'm not going to do it. I'm just going to stick with this. But watch this. I did a direct, so I went through all the scenarios, right? One junior, three seniors, two juniors, two seniors, three, one, four, zero, right? Um, I guess I missed the zero juniors and four seniors at the top, but I kind of just showed you that you could have added, like if you had gone direct, you could have added. I guess this is the direct, sorry. This would be the direct way of doing it. So considering all the scenarios, just one junior or two or three or four, because again, you want at least one junior. So I did not include the zero juniors here when I added. Okay. So instead I chose to go indirect. Indirect reasoning. You want at least two seniors on the team. Okay. I wanted this because it does come up on one of the homework questions that I will assign down the road. At least two seniors on the team. So you would go total. If you wanted to use indirect, I'm going to go no seniors minus one senior on the team. Okay, right? If I do that, whatever is left when I take away the teams that have no seniors and the ones that have just one senior in them, if I take that away, everything else will have at least two senior, right? Two seniors will have two or three or four. So again, this is 9 choose 4 minus no seniors. We're going to go from the 5 juniors, we choose all 4, and from the 4 seniors, we choose 0. Some of you might think this is irrelevant, it's just 1. In a sense, it is, but sometimes it might be a different number, so you got to watch out. 1 senior, from the 5 juniors, we would choose 3, and from the 4 seniors, we would choose 1. Okay, so 9 choose, let's calculate that already, right? 9 choose 4 is just 126 minus 5 choose 4 is, give me 1 second here, 5, sorry, this is 5, 4 choose 0 is just 1, and then here we have, this ends up being 4 choose 1 is 4, and 5 here, so that's 40 actually. I'm just already calculating that. So it's 126 minus 5 minus 40. So that is 81 teams. Okay, just stick with that for now. So a little bit more work, but there you have it. I know it's running a little over, but I'm going to do one more with hands of cards, and that'll be it. Okay. Thank you for writing this down. I appreciate that a lot. It allows me to give you the whole period for quizzes. Okay. Question 3. How many ways can a hand of 5 cards be dealt if there are no restrictions? Now, hands of cards, you should think combinations. Okay. Only difference will be if you end up, if I tell you that it's taken out in the exact order. Yeah, 1 second. All right, hands of cards combinations. The only difference will be if you, for whatever reason, had to line them up to take a picture of it or whatever. But usually, if you just want a hand of cards, it doesn't matter which order they're in your hand. You just use combinations. Order does not matter in this case. Okay. So how many hands can be dealt? And I want to review a deck of cards real quick. So this is my cheat here. There are 26 reds and 26 black cards. Okay. And in each one of those, you've got 2 suits, right? So you've got your for red, you've got your hearts and your diamonds, and you've got your clubs and your spades for your black cards. And for the hearts, you've got ace, 2 to 10, and then jack, queen, king. Ace, 2 to 10, jack, queen, king, and so forth. Okay, every single suit has that. And I would suggest to take a little bit of time and adding this to your study sheet, right? So in total, we've got 52 cards in a deck of cards. 26 red, 26 black. Jack, queen, and king, if you just take, there are 3 in every suit, those we call face cards. There's 12 face cards. And obviously all of them have, right, if you consider the whole deck, there are 4 aces, 4 twos, 3s, and so forth. There's 4 of everything. Okay, so a little deck of cards on the side. Let me just zoom in so you can take a snapshot of this if you want to do that. There we go. So here it is. How many ways can a hand of 5 cards be dealt if there are no restrictions? Finally, we can answer this. Out of 52 cards, we're going to just choose 5. Okay, and that is a big number. That's 2,598,960 hands. It's actually true, right? If you play cards, that's how many hands you can possibly have, where we don't care in which order you're holding the hand. As long as those 5 cards are there, we consider that as 1. We count it as 1. This had been permutation, would have been a huge number. Okay. How about here? And this is where I will change this a little bit. Just this one is a lot of work, but I will give you the answer. Maybe I'll just skip that for now. I want you to focus on this one, and you're gonna have to make a change. Right? How many hands can you have if you must have at least 1 heart? Okay, at least 1 heart. Just write that one down. And if you want to pause and give this a try, you go for it. Okay, so again, the key word is at least 1, not 2. Just want to focus on, this was a little bit, I used to do this, but it's not going to really show up. It would just be a challenge. So you must have at least 1 of the hearts in there. So you would go 52, choose 5, minus. And here you have to be careful. You're narrowing it down to just hearts. How many cards do you have in this compartment? And if you look up there, it's 13 hearts available. So it's almost like your juniors and whatnot. And that means that the rest are 39 others. Okay, I want you to think of it that way. You focus on the hearts, but you also have the others on the deck of cards. So we're going to subtract the hands that from the 13 hearts, we would choose absolutely nothing, just 0. And from the 39 remaining, we would have to choose 5 of those 39 remaining. Okay, for you to, these are the hands that do not have any hearts. Okay, so it's essentially 2,598,960 minus 13 choose 0 is just 1. 13 choose 5, I will have to calculate that with you. 39. Alpha window, 8. There we go. 575, 757. Okay, so it's essentially this minus that, right? I'm going to write it out one more time. Okay, so we're going to go that. So I'm just going to go ahead and subtract it. I know I get a negative, but we know that it's right. 2014, 203 hands. All of these would have at least one heart in them. Okay. How about this? To practice at least one face card. I want to see if you can do this one. If the question asks you how many decks would have at least, or hands would have at least one face card, I'm going to give you the answer in a bit. So you got to know every scenario has its own little perks, right? So this is with combinations. We did some passwords, and we did the true and false or coins, right? So it's kind of like some classic questions in probability as well as here. So this is how many hands. So you would go total minus from the 12 face cards, we choose none, which means that there are 40 that are not face cards. Remember, it adds up to 52, right? Your total is 52. Your hand is 5. This is your hand. And this is the total, your deck. Okay. So that's the dynamic in between here. Thank you very much. I appreciate that. Have a good weekend.